So good evening, everyone. Thank you very much for being here tonight. So as you know, it's the first vLLM and technical meetup in Paris, maybe in Europe, we're not sure, but we're very happy to organize it and to host it tonight. And thank you for being so many here tonight. So it's a technical meetup, but we really wanted to, the philosophy is as follows, is to have an introduction to vLLM and why it's so important in the current stack for generative AI, and to have experience sharing and technical experience sharing from different companies. Again, the philosophy we have is to have someone always that presents vLLM and try to give an update on this open source library, and then to have either hardware providers or model providers that are, of course, highly contributing to this library, and ideally people that are deploying it or having it in production to share real experience from deployment of this library. So thank you very much for all the participants today, especially Grégoire de Turckheim from Scaleway, who has this return of experience deploying on thousands of GPUs. Also, thank you very much, Félix, for being here and for representing the hardware providers and sharing some updates on quantization on AMD GPUs, so the Instinct series. And Etienne, my co-founder, will be presenting an intro to vLLM and share some of the work we are doing on inference optimization. So to present myself as well, so I'm Constant, I'm the CEO of Exxa. As I said, we are working on inference optimization, and we are working mostly with companies to help them optimize the inference on specific hardware, specific models for specific use cases. And today we will really be presenting vLLM and sharing some overview for people who don't know so much about this library. Maybe just before we start, if you could raise your hands, everyone who had heard about vLLM before coming to this event. Okay, so that's great news. Who has deployed vLLM and has actually experienced using vLLM? Okay, that's great. Well, quite many. And who has deployed vLLM in production? Okay, great. That's good. So anyone who wants to share any experience, you're very welcome to do. I don't know if we will have time for spontaneous sharing tonight, but we hope to have other events in the future. So very happy to have you as guests, as speakers as well. Maybe another question, just to know who we are in the audience. Who is coming from Paris, or is based in Paris? So the majority, that's what we're expecting. Anyone coming from a city in France outside of Paris? Where are you from? Grenoble. Grenoble as well. So we are based in Grenoble and Paris as well. So I think it's Grenoble and Paris tonight. Anyone not from Grenoble or from Paris? So very French-based and Grenoble and Paris-based. Okay, so that's great. Just to share an overview of the agenda. So we'll have the talks for around 1 hour, and it will be 20 minutes. 15 minutes presentation and 5 minutes Q&A for each participant. So you can also, of course, feel free to ask any questions you have. And then we'll have from 8:30 to 10 p.m. There will be some pizza coming if everything goes as expected. And of course, we'll have the chance to talk and have some more networking all together. So let's get started. It's a tight schedule, so I think Etienne, you can start.
Hi. So yeah, my duty today to introduce you to vLLM. Well, let's just present myself first. So at Exxa, I'm doing inference optimization. Like that's the main topic of the company. And before that, I led the R&D in a consultancy in Grenoble. For 6 years, and during this period, I also worked on the NPU inference project with ST Microelectronics when they were building their accelerator for their STM32. So yeah, early work on building inference in embedded. That's what got me into inference and optimization itself. So let's jump straight into it. So vLLM as you know it, the goal is to build the fastest and easiest to use open source LLM inference and serving engine. And this is the strongest selling point of vLLM. It's really the easiest path to deploy a shared OpenAI server. Basically, 2 steps: pip install or loading a Docker file and a Docker image, and you can straight up directly launch a server that you will be able to access remotely, and will be shared between different users and fairly distribute the compute between them. That's the point of vLLM, and why it's very important for LLMs to have this kind of shared system, because LLM inference itself loves to be shared. You have a low arithmetic intensity because of the cache caching, which means that this is very reliant on the bandwidth that you can get for your VRAM. Which means you basically need to have your KV cache and your model on high bandwidth memory, which is very expensive. And you also have very large model weights and KV cache, which means that you need expensive memory, but you also need a lot of memory. So you get very expensive infrastructure that you definitely want to share as much as possible. But the challenges that comes from LLM inference get even more challenging with sharing this inference server. So, as with any LLM inference, you don't know the length of a generation ahead of time. It's auto-regressive, so it finishes when the model will output end of sequence token, and before that you don't know what will be the length. And because it's reliant on the maximum bandwidth you can get to be fast, you will want to maximize reading from contiguous memory to obtain the maximum bandwidth. But when you're on the shared inference server, like vLLM, in addition to that, you have requests that can arrive at any time and that can wildly vary in length. And you, of course, have a common compute budget that you need to share and you want to share fairly as much as possible. So that's what led the researcher that worked on vLLM, on the original vLLM paper, to propose two innovations that work together. Continuous batching, that was initially also in the Orca paper, and page attention. So yeah, let's go a bit more into one of the first one. So as I mentioned, the sequence, they can arrive at any time, and they have different length. So with static batching, which was the case in Orca, but before Orca, but also in most deep learning inference servers like Triton, you would have sequences or inputs that you would batch. And the thing is, with autoregressive nature and the varying length of the sequence, you would have like 4 sequences, for example, and then you have one that finishes, and you have underutilization, because now you could compute something at this point, but you because of the way you batch across sequences, you basically lose all this compute. So the idea of continuous batching is to instead of batching across sequence, you batch across token slots, and as soon as they become available, because you have one of the sequence that is finished. Then you will reuse this token slot for another sequence that you get in the queue of requests coming in. So that's the main way that you can share. But if you do that, you still have a problem with the varying length. This is a link to what page attention solved. If you have sequences and you will have tokens generated, you need to have a place in memory to store the KV cache that correspond to this token. And so if you have a given sequence length, like a maximum sequence length and a batch size, maximum batch size, if you don't have page attention, you will need to over-provision the memory, and it scales very fast. So like you will over-provision to the max of the batch size, multiplied by the max of the sequence length, and of course, the weight of one token in the KV cache. Which basically means that, for example, if you have two H100, you will have, if you take llama 70B, you will get 4 sequence at the same time, and not more, because the sequence length is so large at 128,000 that you only get, if you over provision, you only get 4 sequence slots if you want. So this is in fact similar to the memory fragmentation problem in operating system, and that led to virtual memory, and that's basically what page attention is for the KV cache. So it's memory paging to be able to have dynamic memory allocation that is efficient, and to have fast access within a block. Because what you do is you divide the KV cache in logical blocks, and those logical blocks they map to physical blocks in the VRAM, but that don't need to be contiguous. Whereas if you over provision, that's what you would do. So here you basically at one moment you have a different distribution on your physical blocks, and that can be associated to a different number, a varying number of sequences at the same time. So you have a budget of tokens, but you can distribute it over more sequences, shorter sequences, or a few sequences that are long. So this is basically those two things are what kickstarted the vLLM, and it was a research project from the team Skylab, Sky Computing Lab at Stanford, no, at Berkeley. But since then, it grew up into a massive community. You can see the stars on the GitHub repo. But also, it's really like the community build up from model creators, but also hardware vendors. There's like many hardware plugins now being developed to bring all kind of accelerator to vLLM. And as you can see, the contribution are really scaling up, and it doesn't seem to be stopping. And so those two key elements have been since joined by a lot of features that were added by the community. I'm not going to go into those, but they are very important to have an efficient system, state of the art in terms of efficiency. Felix was the next person to present. We'll talk about quantization. Yeah, I will talk a bit about speculative decoding in the rest of the talk. But yeah, don't hesitate if you're interested in one of those to tell us, and we'll see in the following meetups editions if we can deep dive into one of them. So vLLM is not the only way to run LLM inference. You probably heard about many of those names. So we just wanted to give you a kind of a landscape of LLM inference and where vLLM fall into this landscape. This is partly our opinion, and it's also very localized in time because there is a lot of evolution in LLM inference. So yeah, it might not be the same in 6 months, but currently that's how we see things. So vLLM compared to Ollama and Llama C++, which are probably the easier way to run locally your own LLM. The main advantage is just that it's more optimized for shared inference server. Ollama and Llama C++, they come from single user context. They have some kind of server that allows a bit sharing, but they're not optimized for this. TensorRT LLM and NIM, which is more commercial version of TensorRT LLM, in part, is exclusive to NVIDIA, whereas vLLM is open to all hardware vendors. And so currently, already you can use it with AMD or Intel GPUs and much more. And it's adding hardware as it goes, and it's even adding ways for hardware hardware vendors to really make vLLM their inference server for their hardware. So, and then a very large category, TGI, SGLang, and LM deploy. They all have advantages in terms of features, some features that were added in some and not the others. But vLLM here has very strong advantage of having the largest community at the moment. And the interesting thing is that there is a lot of cross-pollination between those servers. They all fall into the same space, and you see features coming in one of them and then being brought by the community into vLLM. So those are definitely interesting to look at also. So there is a very important change in vLLM. Is the change from the version 0 to the version 1. It's ongoing. It's not done yet. But if you use vLLM at the moment, you will have, if you use with default settings, you will probably have already used vLLM v1. It's on by default. But as soon as you have a feature that is not yet ported, it falls back to the version 0. So you have to look out for this warning. But this version is very interesting. This change, because the objective is not so much to change the way you use vLLM, but really to re-architect the core of vLLM to be able to improve first the readability and the ability to contribute from people. So I will give some example on the scheduler and the distributed inference that changed, and also to solve some problems that were linked to the architecture in the engine loop, which is to avoid the GIL blocking the different element of responding to a request. So like the main thing is you see all everything is split into like 3 main blocks that communicate asynchronously, and so you remove the blocking element of an inference. This actually was part of the reason sometimes vLLM would not perform as good as it could, and so this is the first big change in this new architecture. But then there's also two big simplification. First is on the scheduler. The idea is to unify the two major steps in LLM inference, which is the prefill and the decode steps. Here, the scheduler, much simpler than before, unify those two and basically allocate a token budget and distribute it to the different requests. And so you get an output, a dictionary of the number of tokens to allocate to each request ID. This is interesting because first, it's much simpler to understand than what was going on before, but also because it will make easier to develop your own scheduler in the future and adapt it. And so, like for example, we were interested at some point into scheduling at different level of priority. Getting into the old one, the old scheduler, was much harder than getting into this one and building on it. And another simplification that is massive is the way they simplify the distributed inference system. So the idea is that in the V0 architecture, you had one worker, like worker 0, that had the scheduler in it and like some steps that the other worker didn't handle, and it made it more complicated than necessary. So they split the scheduler and they also like kind of duplicated some of the things in the workers, which makes the worker symmetrical behind them, which is way less complex. Of course, like they were doing it for a reason. It was to minimize the communication between the scheduler and the worker, and they solved it in another way by broadcasting the diffs of the request state instead of the whole request state. That was a bit too heavy to be done fast. So. Yeah. So why we are interested in vLLM at Exxa? We help, as Constant mentioned, we help company deploy efficient LLM inference systems, either on-prem, like they are really like their own server, and or on their private cloud. So yeah, AWS, Google Cloud, but with their own deployments. So we wanted to talk a bit about our experience in two examples of working on and around vLLM, because we think that the code base of vLLM might feel intimidating, especially with the V0, V1 going on. Hopefully the V1 is also what will make it a bit less intimidating. But we wanted to tell you that it's very early still, and even if vLLM are already used in production, there is still a lot of work to be done. And interestingly, there is a lot of low-hanging fruit. So it's not like you will have to work for years to really make progress. Like it can go quite fast. And so I wanted to give you two examples of recent work we did that really were interesting for us. So the first one is the recording and replaying workloads. So to give you a bit of context, we want to optimize like deployments, but to optimize deployment, you have to measure how well they're doing. So you have to benchmark different configuration, but it needs to be comparable. So example of comparison that we will want to make is it better to, on this setup, to do tensor versus pipeline parallel, not just from like the ideal point, but like really experimentally, is it better? Is it do we have better result with or without speculative decoding, which I will talk more about later. Is it a good idea on this setup to have priority levels in your scheduler? So all those changes, it's not the only ones, we can think of many. We can benchmark them on synthetic or fixed workloads. That's what is commonly done. The problem is that it's oversimplifying, and for some optimization, it just doesn't take them into account at all. So, for example, like prefix caching and speculative decoding, they're massively underappreciated, if you want, by benchmarks. So, in case of prefix caching, is because prefix caching will only work if in the current KV cache there is an existing request that has the same beginning, the same prefix as the new request, and it will dramatically affect the performance on this new request. So if you do a synthetic benchmark, then you need to do a synthetic benchmark that has those relations, but it will also be linked to the timing between those two requests. If you do a request and then you wait an hour, your old request, the KV cache of this request is probably gone from the GPU. So the prefix caching is not going to be good. So you need the timing, and you need the requests that were done and when, to be able just to reproduce the efficacy of the efficiency of the prefix caching at this time. And speculative decoding, it's even worse because it depends on the state of the server, so the amount of compute that is currently used by the GPU. Because if you speculative decoding is basically trading compute for speed. You compute more, but you get more generation speed. If you're already in a compute bound setting, it's not interesting to do speculative decoding in terms of throughput. So you will lose on other sequences, and but it also is dependent on the sequence itself. Because if you have a model that is trained in English and you have sequences in French, there's no point. You will not predict correctly. So this is why we built recording and replaying. Basically, a reverse proxy in Go in front of vLLM to record everything going in and the timing, and a way to replay by letting a vLLM do the full computation, but we replace the sample token by the next one in the recorded output. So it's computing all of it, but the output is the one we recorded. So just how much yeah. So speculative decoding, just a reminder, it's a way to trade, so compute for speed by predicting a few tokens ahead and verifying with the LLM. But you can verify in parallel, whereas if you do the large model autoregressively, you will have to wait each time that you generate one token to be able to generate the next one. And so that's the other interesting thing that we got from vLLM, is that trying to use speculative decoding on RAG use cases that we wanted to optimize with context size of 4,000 tokens. We wanted to use Eagle 3, and what we got is CUDA kernel crash as soon as the sequence was a bit too long. The generating part, especially, was a pain. And so tracing this, what we found is that, in fact, Eagle 3, the performance are very good, but it's very good in its state-of-the-art speculative decoding model. It's very good, but only when the context size is below 2,000, 2048 exactly, and then it breaks down. So we traced the issue to the model itself that was trained on 2048 tokens. And so from this, we learn, okay, there's an issue that the model now are not where they could be. And so we designed a method to extend the context size of the Eagle 3 models. So here's a small sneak peek of the results. So for long context, here we are 8,000 tokens. We get 2 times more than vanilla. So what we would want with Eagle, whereas Eagle 3 in itself, in fact, is a bit below what the vanilla generation, autoregressive generation, would get. So here is my call for you to get involved in the community. You can, of course, first comment and review the pull requests that are interesting to you, or just put issues on the things that don't work and you would want to work. You can go in, if you want to develop and contribute by developing, you can check out the good first issues. And there's a vLLM Discord and a Slack that we advise you to join. And if we can help in any way in you contributing to vLLM, you can send me an email. And we're also planning on making other editions of those meetups in Paris in September, as Constant mentioned, but also in other cities in Europe. So you can contact Constant if you're interested in attending or presenting at those events. Thank you. And yeah, I'll let you call.
Thank you, Etienne. Maybe because we're a bit behind schedule, what I suggest is that we do a shared Q&A. So we'll have the 3 speakers on stage, and then we can basically share time for Q&A. Félix, if you would like to come, and thank you very much for being here again. Tu peux prendre ça comme micro. Ok. Et passe ça pour les slides, si tu veux. Ou tu peux passer directement. Et c'est le slide à jour. C'est la dernière version. Ok, j'espère. Sinon, tu peux faire des gros trucs. Non, mais sinon, c'est pareil. Merci.
Hi everyone. I will try to keep it short. Maybe, hopefully, not any more than 15 minutes. So I will talk about an optimization technique that is available in most inference libraries, including vLLM, which is Quantization. And it's especially available on AMD GPUs, but other GPUs or devices as well. So when we talk about model optimizations, there are a few metrics we want to look at. And especially we want to maximize our compute, meaning have a high number of operations per second. And so, for example, vLLM does batching to achieve this goal. We want to limit our memory usage because our on-chip memory is limited. So typically, this will hold our model weights, activations, and in the case of autoregressive transformer models, we will have KV cache as well. We would like to maximize our performance per watt or performance per total cost of ownership. So yeah. And finally, among all the optimization techniques that are available, some of them are destructive. And so we still want to keep a high accuracy of the models we will optimize. And the technique I will talk about today is quantization. It's a destructive technique. As you can see in the green here, you have a slight drop in accuracy, but you're able to reduce your memory usage on device and hopefully increase your number of operations per second and have a better performance per watt. So in terms of benchmark, that's about all of what I will present because it's a public talk and I don't have it's kind of a sensitive topic to share numbers. So if you want to look at benchmarks, you can just look on Google and you will find benchmarks between, say, AMD GPUs and NVIDIA GPUs. But I won't present results. So to introduce quantization, I think it's important to introduce what kind of operations happen in deep learning models. And to do that, I took a very toy example, which is a Llama 8B model from Hugging Face Transformers library, running on a single MI300X GPU. And what we can see either here on the host or here on the GPU, in red, you have the operations running on GPU, which are matrix multiplications. And actually what we see is that more than, in this very toy example, we have more than 75% of our time which is spent in doing matrix multiplication. So there is room for optimization, trying to speed up this operator in particular. Now, when you take a model on Hugging Face Hub, so here, for example, a Mistral model, you can look at what is contained inside the checkpoint. And what's in there is actually its tensors. And here we see it's very small, but we see it's in BF16 precision, meaning that each value in the tensor is stored on 16 bits. More precisely, for floating point numbers, so BF16, it's a floating point number, but you also have FP16 or FP32. You will have some of the bits allocated to the exponent, allowing you to have like a wide range of representable values and also a fine-grained representation towards 0, and a mantissa stored on some of the bit widths, allowing you to have some precision as well. And typically, when you will do matrix multiplication inside a network, you will have your inputs activations and your weights in a certain precision, so say BF16, and your outputs in BF16 as well. And for transformer models here, I put in green the operators which do matrix-matrix or matrix-vector multiplication. And that's especially these operators I'm interested about today. So now that we have this context, we can introduce quantization, which is essentially using lower numeric precision to either store our weights or tensors, or even better, if we can, to do like computation. So for example, you have FP8, which uses a smaller number of bits for exponent and mantissa, or int8, which is slightly different in the sense that it's usually used as a uniform quantization scheme, where you take your original weights distribution and have only a few limited number of quantization bins you will round your high precision values into, simply as a step function. More precisely, this scheme is it's probably the most common one. It's not new at all. It's maybe 10 years old or even more for deep learning models. When you use integer uniform quantization, you will have two hyperparameters. The most important one being the scale, which represents the distance between two representable quantized values. So here you have WQ, which is your quantized value within a it's like your quantized tensor, and W your original tensor. And we see that when you increase WQ by 1, you will move by your scale. So it's like it's a distance between two quantized bins. And you also have, in some cases, a 0 point, which allows you to shift your quantized range towards the negative or the positive in case the distribution you're trying to quantize is not centered on 0. And so what's interesting about this is that if you take a high precision matrix multiplication C equal A times B, and if you rewrite it, you can factor out the scales, and you come out with AQ, BQ, a matrix multiplication with integer values. And so if your hardware supports integer arithmetic, maybe you have some chance that doing integer arithmetic will be faster and also consume less memory than using floating points, especially in high precision. Okay. Okay. Now, when it comes to autoregressive transformer models, you have different tensors that you hold in memory. And you can say, I want to quantize some of them, and some of them I don't want to. And the first thing that you could do is quantize your weights. It allows to use smaller checkpoints because, yeah, you use, say, 8 bits to serialize a single value instead of 16. But also, when you store your weights on device, you have a lower memory requirement. However, if you don't quantize your activation at the same time, it could be that you have mixed precision during inference. You have your weights in, say, FP8, and you have your activations in FP16. And it's not completely trivial to implement like a matrix multiplication, which does a multiplication between D types with inputs having different D types. So one good thing would be to quantize activations, and in some cases, so for example, if you run on AMD MI300X GPU or NVIDIA Hopper, NVIDIA Blackwell, you could actually run your gem on FP8, for example. But the drawback is that you need a calibration to have these scale and possibly 0 points for your activations. So either you can do that offline with calibration dataset, passing it through your network, or you could do it online during inference using dynamic quantization. You could also quantize your KV cache in case you are bottlenecked by your on-device memory, and especially if you're dealing with long sequences, and want to be able to process more tokens in one time. And finally, in case of vLLM, you can use multiple devices to deploy your model using tensor parallelism. And when you use tensor parallelism, you will need to have some collective ops. And in some cases, it could be interesting to quantize the members of collective operations in case you are bottlenecked by the inter-device communication. So when it comes to vLLM, there's a very good documentation page about quantization that I recommend to read. vLLM mostly supports offline quantization, meaning that you will need to quantize your model ahead of time, offline using an external library. But you also have some publicly available open source models, and I would definitely recommend the Red Hat validated models. But you can also find some from AMD or some models which are natively released in low precision. Okay, so on this slide I put some example of popular quantization schemes. So the first one I mentioned is weight-only quantization, and it includes quantization algorithm like GPTQ or AWQ. Maybe you heard of those. And I put some example commands. So essentially you just need to pass the name from a model stored on HFHub or stored on your local machine. And vLLM would automatically detect that this model uses a certain quantization scheme given the configuration file in the model repo. This one, weight on 8 bits, activation on 8 bits, and especially FP8, is getting quite popular, I would say, because it's typically it's not, I mean, it's destructive, but the cost of doing it in terms of accuracy is very low, especially on when you use large models. And even going lower on using weights on 4 bits and activation on 4 bits, if you look at Blackwell, NVIDIA Blackwell architecture or CDNA for architectures from AMD, there is a push towards using NVFP4 for NVIDIA or MXFP4 for AMD. Because again, if you look at submissions at MLPerf, the accuracy cost of using these precisions, even though the models were trained in BF16 or FP16 or FP8, you can get still very good predictive performance, even using weights in 4 bits and activations in 4 bits. Okay. So yeah, maybe you don't know AMD GPUs, but the current architecture, which is widely available on cloud, is CDNA 3, especially MI300X and MI325X, supporting int 8 and FP8. And it was announced this month, CDNA 4, with MI350, supporting FP4 and FP6. Okay, this I will skip. Okay, why am I talking about quantization? It's because I work on an AMD library which is called Quark. And it's a library meant for model optimization and especially geared towards quantization and pruning. It's open source, but the development is done privately. And it's especially focused towards AMD devices like CPUs, GPUs, and NPU. Yeah, and finally, I want to mention that maybe you saw this on LinkedIn already or not. AMD is organizing at Station F. It's a coincidence, but this weekend, a hackathon. Actually, very close to the topics we are discussing today, because it's about optimizing serving libraries like vLLM on AMD MI300X GPUs. There are some race tickets giveaway. I don't know what that is, but apparently there's some AI conference next week or something. And apparently AMD gives away some tickets. And there's also some prize money from the hackathon. So hopefully if you want to register, I put the link here, and I think there's still room to accommodate people. Thank you.
Thank you very much. As before, please keep in mind your questions, and we'll have time after the last talk to go through them. And now I will invite Grégoire to come on stage and share some more, let's say, real-life experience deploying vLLM and some of the challenges I think that you experienced at Scaleway.
Thank you very much. So now the smart guys have gone. You can switch your brains to low-power mode, and we'll have some fun deploying vLLM and having problems with it. So I'm Grégoire, I'm an engineering manager at Scaleway, and I'm working on platform as a service AI products. We also have big clusters product with thousands of the GPUs if you have millions in your pockets, but I don't think you do have that tonight, unfortunately for me. So we'll keep on the platform as a service products. So the talk is called vLLM OpenAI latest, and the latest part is really important. We're not doing a hidden advertisement at Scaleway, so I'm doing it right in your face. We currently have 2 products, inference products at Scaleway, generative APIs and managed inference. The first one is built by the token, and the second one is built by the capacity. And when we had this journey with inference, we started like many companies. We were sold something by NVIDIA. And we were sold their Triton server and TensorRT LLM and blah, 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 the whole stack going with the GPUs. And we spent a few months realizing that we needed to ditch it. So that's what we did. It was painful, but we did it. And we found out that vLLM is incredibly easy to start with. As it has already been said, just add a dash model, almost anything, and that works. And that is amazing. You can spray some Kubernetes magic on top of it. And that's it. You have a almost production-ready product. And that's what we're going to talk about today. So, first thing I wanted to say is vLLM, but it's not specific to vLLM, but any inference product is hard to monitor and tune. For the monitoring parts, you'll be seeing some strange metrics going all over the place, and you'll have a really hard time understanding what's going under the hood. So really be prepared for it. And if I have one piece of advice for you is know your workload, okay? We, as an inference provider, have a big problem. We don't know what customers do with our product. So we need to handle any kind of workload. It could be 10 tokens or 100,000 tokens in a single request. You have to handle them very differently. And it can be very difficult to manage any possible combinations and models. And tuning the thing, there are lots of parameters. This is actually the documentation. I'm not joking. They changed recently the page for the documentation. So documentation is now being written as Python code. It's really hard to understand. There are many different parameters. And so once again, if you know your workload, it will be pretty easy to find the right parameters that you want to use, and it will be easy to tune. If you don't know your workload, you're going to have some hard time. Then, once you have a product, customers kick in. And that's becoming a real challenge. So we have something called Scaleway feature requests, and customers enjoy playing with it, and they want more and more models, more models, more models. I especially like this one. The guy said literally, hey, please add more models. Tell us what you want, guy. Come on. So we try to find a way to move from the sets of models that we curated and offered to our customers to more models. And some guy came with a stupid idea and said, hey, we can allow customers to bring their own model. Before, we had 32 models. Now, customers can import like more than 1.5 million models. See the difference? And some guy in the product division said, hey, yeah, that's a really good idea. Let's go for it. So many GPUs, many models, many vLLM versions leads to big headaches. So, how can we do? First, try to tell the customers, hey, what you're trying to do is not possible. It's not an LLM, it's not transformer model, it's you cannot do that. So don't do it. So we have like zillions of possible error message that we extract from vLLM logs, like, we try to find the exception messages in vLLM and translate them to something the customer can be able to understand. And we have lots and lots and lots of them. Actually, to extract those, we run the top 1,000 models on Hugging Face and collected all the crash logs to extract those. Enjoy. Next thing is that even if you do all of this, at some point, you will end up with exceptions in vLLM logs. So there are easy ones. Usually they come from Mistral. Mistral, they just do something on the side, so they don't take the regular path. So you will always have slight problems with Mistral models. We love them. They do excellent models, but they always do it on their way. Then you'll find much harder ones like, hey, I ran out of memory. Come on, you've been running millions of inferences for days, and now you're running out of memory? Yes, sure. Why not? And there's no real way to predict how it will behave and how much memory you really need to support one model or another. So be prepared for that, and be prepared to leave some margin just in case. And there are like very funny catastrophic ones. This one we actually had a few days ago. A customer sent, he was trying to have a structured output. So he sent his JSON schema and his requests. And the vLLM said, oh, this schema is invalid. And then, engine dead error. Why? Just because of that, it got stuck. Like, there was one query still running for hours. And it would say it is alive on the health endpoint, but it stopped working, just at the random. So be prepared for that, or just select a few models and stick with them. And I'm almost done. The closing thoughts, what we can learn from that is that models, and by extension, inference engines, are made by researchers, data scientists, and DevOps that are in the data field. So they're not used really to do code that is run on a massive scale, that is well instrumented. We've talked already about that. vLLM is a recently new piece of software, so it has to be given some time to mature and to enjoy some more robust error handling and this kind of stuff. My previous product at Scaleway was running serverless Postgres. So I can tell the difference between a 2-year-old product and a 40-year-old product. There's very few standards. The dust hasn't settled yet. You will find models with this and this and this kind of capability. And so you always have to run on the edge. You always have to run vLLM latest, because when the next cool model is released, and customers will obviously want it, and the support will be in vLLM, would have been merged in vLLM like 3 days ago. So you really always need to be on the edge. The LLM world and the AI world goes really, really fast, and you need to stick with that. So yes, the code is not yet really, really production ready. You can do some production with it, but you have to be prepared for a lot of run on that. And as I said, you are building on quicksand, so everything is moving. New technologies appear every week. You don't know which one will be ditched in 3 months, so you have to be very agile and be prepared for constant evolution and constant switching of switch your sides and go this way and go through that. And one last closing thought is that vLLM is cool. It's very cool. It's amazing technology. But LLMs is not all of AI. Depending on your use case, you will need image generation, video generation, sound generation. You will need some predictive models that are not outputting texts, that are not transformers, that are not whatever. And maybe you will need several inference engines. So getting several engines in parallel may be hard to achieve depending on your use case, so be prepared for it. Sometimes you need more than just LLMs. That's all, folks. Now you can switch your brains back on.
Thank you very much. As I said, let's have a Q&A and maybe all the speakers together on stage. Okay.
Does this work? Do you hear me? Yeah. Okay. Thanks. Thank you all for the presentations. It was very informative. I have a question for Etienne regarding vLLM and the new architecture of vLLM. It's now deployed in scenarios where it's not inference only, like for example for training reinforcement models. It's used to generate like an inference engine in a training setup. From my experience, it's a little bit well. The architecture of vLLM being multi-process, etc., adds some overhead in serialization, etc. And in process, having an in-process inference engine that is as performant and based on page attention, etc., could be a way forward. And I don't see this in the architecture of the V1, nor is it the target of the whole project to build a multi-threading based, for example, inference engine that is self-contained, maybe doesn't depend on Python, and maybe is fast to run in an environment that you need that speed and no additional overhead.
Yeah, so definitely there's trade-off, and they made trade-off, I think, for really like for inference and like as many users as possible. I think they're really going more and more. The project is going more and more in the large setups. I only talked about the simplification part. There's also things linked to disaggregated prefill, and all of this is going on at the same time. I think it's really what is it's most worked on. But I know that some are also using it for other projects. Yeah, that there's a. Yeah, I agree that the question is, will you be able to use it for those things? There is a project that is interesting to understand how vLLM works, and that also has different trade-offs. Is nano vLLM, which is very recent. And I think that might fit the bill for reinforcement learning and data generation in this context. It's less complex and it's much more hackable. So if you don't need the large setup, I think there might be like kind of a vLLM light that might get on.
Okay, thanks. Quick follow-up question. Now it's for the AMD side. I do have a question about quantization performance for models that are trained on FPH, for example. We saw the DeepSeek paper, and they actually trained it in FPH from the start, and they showed that it has a better quantization capability, for lack of a better word. What do you think about that? And is there some post-training way of achieving better model quantization and not just computing at some scale? Thanks.
There's a trend towards using lower bit widths in training as well. So if you look for papers for FPH training is not new, but there's even recent papers about doing training in FP4. Since you have like Blackwell, CDNA4, support MXFP4 and GFP4. So some people are looking into using that for training as well.
Yeah, okay, so it's definitely better for quantization later. Yeah.
Yes, but it's also much more expensive and more tricky. Like if you're a company and you want to fine-tune models, you probably maybe don't have the capabilities to actually do quantization about training, and it's maybe a little bit easier to take existing models and apply post-training without gradient descent, taking into account the quantization effects.
Thanks.
Thank you very much for the presentation. That was, yes, I'm here. That was really interesting. Hello. I was just, at the moment, vLLM is quite, it takes a lot of time to boot, and it makes serverless inference impossible. Do you see a future in which, like a close future, obviously not in 5 or 10 years, a close future in which serverless inference is possible? And what do you think are the techniques involved? Is vLLM just gonna get better at that, or are we gonna see snapshotting of the memory or something like that coming soon? Thank you. And yeah, I don't really know who my question is directed to.
I'll take it. I think that for now, in the short future, it's going to be a bit worse because they're extending the use of Torch compile, and Torch compile is run at the start of the server. Maybe in the future we'll have some kind of ahead of time compiling and snapshotting of those CUDA graphs, and a way to speed up. There is a way there is some plugins that allow you to speed up the loading of the weights, so that can be improved. But yes, like serverless inference, you're always going to have quite a large cold start. Just like you need to also take into account that those models are very large. So if you're in a serverless setting, you will need to download or have a local disk. So not really serverless, and you will need to charge those weights in the memory. So it will take at least some time. So much more cold start than in other serverless workload. And yeah, I think it's going to get worse before getting maybe better, but with techs that I don't know of yet.
Agreed.
Hello, just over there. Yeah, thank you very much for the talks. I have 2 questions. First, for the first and third speakers, will you open source reverse proxy code in Go and the logs that have been mapped to intelligible logs?
So, if people are interested, then we might open it. Sure. The workload, well, it depends. Like maybe we could work on an open dataset, but the dataset that we build for our clients, those cannot be open sourced, of course.
Yeah.
Because yes, like we store the content of the request. We also build a way to not store the full request, but still have the way to link requests together and kind of simulate prefix caching, etc. With hashing of part of the sequence. So yeah, definitely something we're open to, open source.
And for the logs at Scaleway?
Yes.
Well, we could do that, but I don't think this has much value. Mainly because the error messages change constantly within the vLLM code base, so we would need to keep this up to date forever. And at some point it will be useless because there will be much better error handling in vLLM. And I don't see Scaleway open sourcing error messages anytime soon. But yeah, we could do that, but I don't see much value into that.
So why did you do it then?
Because we need to inform our customers, but that's a very small piece of the big puzzle.
Okay. And sorry, and I have a second question for AMD. It's very practical. So you mentioned like different quantization where we could quantize a KV cache input activation. Based on your experience, where we should like look into to maintain performance and.
Yeah. I mean, it really depends on your workload and your use case. it really depends. Like if you're serving only one or a few requests at a time versus 1,000 requests at a time, you will need to do things differently. So yeah, it's not a one solution fit all. I would say, like for example, if you serve only a few requests at a time, you will be most likely memory bound, since you need to reload weights into your close to your compute unit at each autoregressive step. And so doing weight only quantization could be easy, and if you have kernels supporting that, could be interesting to do.
Okay. Thank you.
Thank you for your presentation. I have one question for Félix. I'm here. You mentioned MXFP. Is it blocking floating point? And if so, can you explain what's the benefit of using them?
Yes, it's like per group quantization, where you have one scale per group of 32 values in your tensor. And NVIDIA has an equivalent. And it's interesting because when you look at the instruction set architecture from CDNA4, you have some matrix core instructions, meaning that you can take a small piece of matrix A, small piece of matrix B, scale of A, scale of B, and have a single instruction doing a small matrix multiplication on chip. So I don't know exactly, but I guess you have on the silicon you have an implementation of a small matrix multiplication, and so if we are able to don't lose too much in accuracy using this kind of low precision data types, maybe it takes less space on silicon and less memory as well. So.
Okay, thank you. I think I have another question, which is for FP8 or even FP, not sure about FP4, but for FP8, I think there's at least 2 representations that are possible.
Yes.
Can you tell us about them and whether there's one which is more used than the other?
So you can. It's kind of the same thing than FP16 and BF16. You allocate a certain number of bits to your exponent and a certain number of bits to your mantissa, and so you trade off like the range and the precision, and depending on your use case, one of the two might have you might have better results using one of the two. I think for inference with FP8, E4 M3 is the most common one, but I didn't really benchmark both, but yeah.
Okay, thank you.
Yes, any other question? I see someone there.
Thank you. My question is there tools, even in early stages, to do same techniques we already use in hardware optimization use, tools for saving the full context of an execution on hard disks, and a quick load of a context. Donc, the question is for share the resource, the hardware resource, within multiple applications.
So you mean the KV cache, offload the KV cache to disk?
Yeah.
Yeah. So yes, that's something that can be done. Of course, the question is then, can you load the KV cache faster than you can recompute, redo the prefill? Yeah, there's it's quite involved, and then I think in smaller, like relatively small setups, it's quite difficult to load the KV cache fast enough to be that interesting. But for larger scale, it's much more interesting. I think it starts to be very important in those situations. But yeah. you might have more input on this than I have.
No one else. So we are. I mean, I'm the only thing remaining, like stopping you from going to the pizza. So I don't know if there is maybe one more question. Yes, and then we. Yes. Just one question.
Thank you. So recently there was an announcement about LLMD that sits on top of vLLM. Can you maybe share what the value of LLMD compared to vLLM?
So once you get into setups that needs more than one node, you have additional problems to handle. First is route your requests between the different nodes, different like servers, and you also have new opportunities to optimize. And one of them is to distribute the different phase of the inference among those nodes and or nodes or GPUs. And the main thing is like the disaggregated prefill and decode, and those are very interesting for large scale inference systems. But yeah, and so like LLMD, it really helps in those things. So handle the problems that comes from multi-node, and also implement or help implement new optimizations that are really related to larger scale deployments. So that's why it makes sense to be on top. You might have heard also NVIDIA created a library called Dynamo that is related to this, and I guess we will see more of this come in the future. It's in the same space, like make it easier to do larger scale inference systems.
Thank you very much. Before we go to the dinner, just first of all, thank you very much for the speakers. And for your questions as well, of course. So just one last comment. We are looking for new speakers. So again, if you want to share anything technical about this in the coming months, we'll organize similar meetups. The next one will be in September, here as well, probably. The second thing is that we might contact you just to get some feedback to improve it. It's the first edition, so of course we very appreciate any feedback. And now we can all go to the pizza. We have the room until 10 p.m., so we got an extension for 1 hour, so we have plenty of time. And yes, we're happy to answer any questions. Thank you.
Thank you.